Dimensional analysis and modeling. This topic introduces dimensional analysis and modeling as fundamental tools in fluid mechanics to simplify and understand complex physical phenomena. This approach allows relationships among physical variables to be derived without solving detailed differential equations. The main focus is how physical quantities can be grouped into meaningful dimensionless parameters. In this way, experimental results can be generalized and applied to different system scales. This chapter forms an essential foundation for understanding similarity between models and prototypes.
Lesson Plan Fluid Mechanics 1. The course structure shows that this topic comes after momentum and energy analysis, serving as an integrating tool for previous concepts. Each earlier chapter provides the physical basis used in dimensional analysis. Placing this chapter before internal flow highlights its role as a bridge between theory and experimental application. By understanding this sequence, students can see the logical progression of the material. The whole curriculum is designed to build understanding step by step, from basic concepts to advanced applications.
Learning outcome. The learning objectives emphasize mastering dimensions, units, and dimensional homogeneity as the basis for validating physical equations. In addition, students are expected to understand the practical benefits of dimensional analysis in simplifying engineering problems. The method of repeating variables is introduced as a systematic tool to find dimensionless parameters. The concept of dynamic similarity becomes the key to linking experimental models with real systems. The final outcome is the ability to apply these concepts to fluid flow modeling.
Dimension and unit. A dimension represents the type of a physical quantity without involving specific numerical values. A unit provides the numerical scale so that the quantity can be measured and compared. For example, length as a dimension can be expressed in different units, such as meters or centimeters. Separating the concept of dimension from unit is important to maintain consistency in physical equations. With this understanding, conceptual errors in engineering calculations can be avoided.
Surface tension and water strider. The phenomenon of insects walking on water shows the important role of surface tension in fluid mechanics. Surface tension acts like an elastic membrane that can support light loads. The distribution of weight through the insect's legs prevents penetration into the water. This example connects abstract fluid properties with real natural phenomena. It also emphasizes that certain physical parameters can dominate system behavior at small scales.
Check your understanding number 1.
This question tests the basic understanding of the role of the liquid surface in the surface tension phenomenon. The focus is on identifying the part of the fluid where the force acts. By answering it, students reinforce the link between physical concepts and real examples. This short check serves to strengthen understanding before moving on to dimensions and similarity. Such quick evaluations help ensure that conceptual understanding is not missed.
Primary dimensions and units. This explanation reiterates the relationship between each primary dimension and its units in two measurement systems. Consistent use of units helps avoid numerical errors in engineering calculations. Although unit notation may differ, the physical meaning remains the same. This reinforces the idea that dimensions are more fundamental than units. With this basis, dimensional analysis can be applied universally.
Consistency in measurement. The principle of consistency emphasizes that only quantities with the same dimensions can be added or compared. Mixing different quantities, such as length and mass, leads to logical errors. Simple analogies like adding apples and oranges help clarify this idea. In engineering equations, this rule becomes a quick tool to check the correctness of a formulation. By maintaining consistency, the physical meaning of equations is preserved. Energy states in a system. The energy of a system at a given state consists of internal, kinetic, and potential energy. Each system state can be represented as the sum of these energy components. By comparing two states, the change in system energy can be analyzed quantitatively. This approach forms the basis for energy analysis in fluid mechanics and thermodynamics. The concept of energy states must also satisfy the principle of dimensional homogeneity.
Dimensional homogeneity. Dimensional homogeneity means that every term in an equation must have the same dimension. If one term has a different dimension, the equation is physically wrong, even if it looks numerically reasonable. This principle becomes a quick checking tool to validate derived or used equations. In engineering practice, many conceptual errors can be detected simply by checking dimensional consistency. Therefore, dimensional homogeneity is a mandatory requirement for physically meaningful equations.
Check your understanding number 2. Why is dimensional consistency important in formulating equations in engineering? B. It guarantees that the equations are physically meaningful and relevant to the system being analyzed. Explanation. A is incorrect because dimensional consistency does not ensure numerical equality, but ensures that terms have compatible dimensions. C is incorrect because dimensional consistency is a validation step, but does not eliminate the need for further checks. D is incorrect because dimensional consistency does not reduce the number of terms. It ensures the terms are compatible within the equation.
Bernoulli equation insights. The Bernoulli equation is a classic example of a dimensionally homogeneous equation. Each term represents a form of energy per unit volume, or pressure. Since all terms have the same dimension, the equation is consistent and physically meaningful. This shows that dimensional homogeneity is not just a formal rule, but is embedded in physical laws. In this way, the validity of the equation structure can be more deeply understood. Non-dimensionalized Bernoulli equation. By dividing each term of the Bernoulli equation by a reference pressure, a dimensionless form is obtained. This process removes units while preserving the physical relationships among variables. The result is a more general equation that can be applied to various flow conditions. This approach makes it easier to compare systems of different scales. Non-dimensionalization becomes an important step in similarity analysis and modeling. Object falling in vacuum. The motion of an object falling in vacuum is used as a simple example to discuss sign conventions and the effect of gravity. The vertical velocity is defined as positive upward and negative downward according to the chosen convention. Gravitational acceleration always acts in the negative vertical direction. With this definition, the equations of motion can be written consistently and analyzed easily. This example also shows the importance of agreed directions in physical modeling. Fluid flow parameters. In fluid flow problems, characteristic length, characteristic velocity, and pressure difference are usually chosen as the main scales. In addition, fluid properties such as density, viscosity, and gravitational acceleration influence the flow behavior. The selection of these parameters aims to simplify the problem without losing its physical meaning. With this approach, complex systems can be represented by a small number of key parameters. This is the basis of scaling analysis and modeling.
Slide 17. Check your understanding number 3. This question reinforces the main parameters used in scaling fluid flow problems. The focus is on recognizing pressure difference as an important scale besides length and velocity. By answering it, students strengthen their memory of the basic framework of scaling analysis. Such short questions help maintain continuity of understanding before moving on to dimensionless numbers. This small evaluation serves as a concept lock.
Froude number in open channels. The Froude number is used to characterize flows with a free surface, such as in open channels. Its value represents the ratio between inertial and gravitational forces. In the case of a sluice gate, the upstream and downstream Froude numbers can differ because the flow conditions change. This information is used to determine whether the flow is subcritical or supercritical. Thus, the Froude number becomes a key parameter in free surface flow analysis.
Advantages of non-dimensionalization. Non-dimensionalization helps identify the relationships among key parameters in a problem. The number of variables that must be studied can be significantly reduced compared to the original form. This makes the analysis simpler and the results more general. Equations in dimensionless form are also easier to compare across systems of different scales. These advantages make non-dimensionalization a very powerful engineering tool. Ball trajectories in vacuum. By non-dimensionalizing pine and height, ball trajectories can be generalized into a single plot. Different values of the Froude number produce different trajectory shapes. This presentation allows many initial conditions to be compared within the same framework. This approach demonstrates the power of dimensionless parameters in unifying various physical cases. The result is a broader understanding of system behavior. Scaling in fluid flow. In fluid flow scaling, several key parameters such as characteristic length, velocity, frequency, and pressure difference are used to describe the system. These parameters are then summarized into dimensionless numbers such as Reynolds, Froude, Strohel, and Euler. Each number represents a ratio of certain types of forces or physical effects. By using these numbers, flow behavior can be understood without depending on absolute units or scales. This approach makes flow analysis more general and flexible. Kinematic similarity. Kinematic similarity means that the flow pattern in the model and the prototype has the same geometric shape. The velocities at corresponding points must be proportional to each other. In addition, the flow directions in the model must match those in the prototype. If these conditions are satisfied, the trajectories of fluid particles will be similar in both systems. This concept becomes one of the important requirements before discussing dynamic similarity. Check your understanding number 4. What is a key requirement for ensuring similarity between a model and a prototype in fluid flow analysis? B. The flow speeds at corresponding locations must be proportional between the model and the prototype. Explanation. A is incorrect because the model and prototype do not need identical dimensions. Scaling ensures similarity. C is incorrect because identical temperature conditions are not always required as long as the scaling laws account for temperature effects. D is incorrect because the fluid properties can differ as long as dimensionless parameters like Reynolds number are matched. Geometric similarity. Geometric similarity means that the model and the prototype have the same dimensional ratios in all directions. Every length in the model is a fixed scale of the corresponding length in the prototype. As a result, the overall shape of the system is preserved, even though the size is different. Without geometric similarity, other types of similarity cannot be achieved. Therefore, this is the most basic requirement in physical modeling. Reynolds number. The Reynolds number is defined as the ratio of inertial forces to viscous forces in a fluid flow. Its value depends on density, velocity, characteristic length, and dynamic viscosity of the fluid. This number can also be written using kinematic viscosity in a simpler form. The Reynolds number is used to classify flow types, such as laminar or turbulent. In modeling, matching the Reynolds number is often an important requirement for dynamic similarity. Drag balance in wind tunnel. This device is used to measure aerodynamic drag forces on a model inside a wind tunnel. A moving belt is installed to simulate ground motion relative to the vehicle.
In this way, the flow conditions around the model become closer to real conditions. The measurements allow aerodynamic performance to be evaluated under controlled settings. Such facilities are very important in vehicle design development.
Prototype and model dynamics. Dynamic similarity requires that the forces acting on the model and the prototype have the same ratios. For airflows, this means that density and viscosity must be matched or compensated through velocity scaling. The model velocity is usually adjusted based on the length scale ratio between the model and the prototype. If all similarity conditions are satisfied, the drag force on the model can represent that on the prototype. Otherwise, the test results can be misleading.
Check your understanding number 5. This question reinforces that dynamic similarity is not only about shape, but also about fluid properties. The key phrase in this problem is the matching of fluid properties and scaling between the model and the prototype. By answering it, students strengthen their understanding that the acting forces must be proportional. This question also reconnects the concept of Reynolds number and other dimensionless numbers. This short evaluation helps lock in an important concept before moving further. Achieving dynamic similarity. Dynamic similarity can still be achieved even when the model and the prototype use different fluids. The key is to adjust the scaling parameters so that the relevant dimensionless numbers remain the same. For example, a submarine model can be tested in air with appropriate scaling adjustments. This approach makes testing more practical and economical. In this way, the behavior of the real system can still be predicted reliably. Method of repeating variables. This method begins by listing all parameters that affect the problem, along with their dimensions. From this list, the number of dimensionless groups to be formed is determined. Then, several parameters are chosen as repeating variables to construct the pi groups. The final result is a functional relationship in terms of dimensionless parameters. This method provides a systematic procedure for performing dimensional analysis on complex engineering problems. Steps for repeating variables. The first step is to identify all independent and dependent parameters along with their dimensions. After that, the Buckingham pi theorem is used to determine the number and form of the dimensionless groups. Repeating variables are then chosen to construct each pi group systematically. The obtained results must be checked again to ensure that they are truly dimensionless. With this procedure, complex physical relationships can be simplified in a consistent way.
Check your understanding number 6. What is the primary purpose of the Buckingham pi theorem in fluid mechanics? B. To determine dimensionless groups that simplify the relationship between independent and dependent parameters. Explanation. A is incorrect because the Buckingham pi theorem does not eliminate parameters but organizes them into dimensionless groups. C is incorrect because it is not primarily used to identify errors in parameter listing, but to simplify relationships. D is incorrect because while dimensional consistency is important, the theorem's focus is on forming dimensionless groups, not unit validation.
Ball motion in vacuum. The motion of a ball in vacuum is used as an example of applying dimensional analysis to a classical mechanics problem. The height of the ball depends on time, initial velocity, initial position, and gravitational acceleration. All these variables can be combined into dimensionless groups to simplify the analysis. With this approach, the motion behavior can be presented in a more general way. This example shows how the method works on a simple system. Exponent rules. Exponent rules are used when constructing and simplifying the algebraic form of pi groups. When two terms with the same base are multiplied, their exponents are added, and when divided, the exponents are subtracted. These simple rules are very important to ensure that the final result is truly dimensionless.
Small mistakes in exponent manipulation can produce incorrect groups. Therefore, algebraic accuracy is crucial in dimensional analysis. Choosing repeating parameters usually involves length, velocity, and mass or density in fluid flow problems. These parameters often appear in many dimensionless groups. Proper selection simplifies the process of forming pi groups. If chosen poorly, the analysis can become complicated and inefficient. Therefore, the strategy of selecting repeating parameters greatly affects the ease of the analysis.
Guidelines for repeating parameters. Dependent parameters should not be chosen as repeating parameters because they would break the structure of the analysis. In addition, the chosen parameters must together represent all primary dimensions involved in the problem. It is better to choose parameters with simple dimensional forms rather than complex combinations. These guidelines help keep the process systematic and clean. By following these rules, the formation of pi groups becomes more controlled.
Check your understanding number 7. This question tests whether students understand which type of parameter should be avoided when selecting repeating variables. The correct answer emphasizes that dependent parameters must not be used as independent variables in forming pi groups. By answering it, the structure of the Buckingham pi method is reinforced. This problem also prevents a common mistake often made by beginners. This short evaluation serves as an important reminder.
Dimensionless groups. In forming pi groups, all exponents of the primary dimensions are forced to be 0. In this way, each resulting group truly has no units. This method guarantees that the final results are purely dimensionless. These groups are then used to express the functional relationships among variables. This approach ensures physical consistency in the analysis results. Naming non-dimensional parameters. Many dimensionless parameters are named after scientists who made major contributions to their development. This naming reflects historical and scientific contributions in fluid mechanics and engineering. Examples include Reynolds, Froude, and Mach. By recognizing these names, students also become familiar with the history of scientific development. This shows that scientific progress is built through the contributions of many individuals.
Guidelines for manipulating pi groups. Pi groups can be raised to powers or inserted into mathematical functions without changing their dimensionless nature. They can also be multiplied by pure dimensionless constants, such as pi or 2, without affecting their physical meaning. Several pi groups can be combined through multiplication or division to form more familiar expressions. Dimensional parameters inside pi groups can also be replaced by other dimensionally equivalent parameters. All these manipulations aim to produce forms that are simple and easy to interpret physically.
Common dimensionless numbers. Various dimensionless numbers are used to represent different physical phenomena, both in heat transfer and fluid flow. Numbers such as Reynolds, Froude, and Euler compare different types of forces acting in a flow. Meanwhile, Biot, Fourier, and Jakob are related to comparisons of thermal resistance and heat diffusion. There are also numbers that compare gravitational and surface tension effects, such as bond and capillary. This classification helps in selecting the relevant parameters for each engineering problem.
Check your understanding number 8. What does the Biot number primarily represent in heat transfer analysis? B. The ratio of thermal resistance within a solid to the thermal resistance at the surface. Explanation. A is incorrect because this describes the Froude number, not the Biot number. C is incorrect because this represents the bond number, which compares surface tension and gravitational forces. D is incorrect because the ratio of energy conduction to storage is represented by the Fourier number, not the Biot number.
Extended dimensionless numbers.
Besides the commonly used numbers, there are many other dimensionless numbers applied in heat transfer, flow dynamics, and mass diffusion. Numbers such as Nusselt, Prandtl, and Peclet link convection, conduction, and diffusion. Mach, Weber, and Stokes are related to flow speed, surface tension, and particle motion. Schmidt, Sherwood, and Stanton are used to analyze mass transfer. This variety shows how wide the application of dimensionless concepts is in engineering.
Verifying dimensionless parameters. Each obtained pi group must be checked again to ensure that it truly has no units. In addition, the algebraic manipulations performed during the process must also be verified to avoid errors. Small mistakes in algebra can lead to wrong physical conclusions. Therefore, this verification step is just as important as the group formation step. With careful checking, the reliability of the analysis results can be maintained.
Pressure in soap bubbles. The pressure inside a soap bubble is higher than the outside pressure because of surface tension forces. This tension acts along the film surface and creates an inward force. The film thickness and bubble radius influence the magnitude of the pressure difference. Smaller bubbles have higher internal pressure. This example shows the dominant role of surface forces at small scales.
Check your understanding. Number 9. This question tests whether students understand the physical cause of the high pressure in small bubbles. The key answer is the surface tension forces acting along the surface. By answering it, the relationship between surface forces and pressure becomes clearer. This problem also reinforces the understanding of dominant effects at small scales. This short evaluation helps lock in physical intuition.
Handling zero pi groups. If a pi group turns out to be zero or meaningless, the list of parameters must be checked again. The error may come from the choice of parameters or from algebraic mistakes. In such cases, the number or selection of repeating variables needs to be changed and the process repeated from the beginning. This approach ensures that the final results remain consistent and meaningful. This correction step is a normal part of the dimensional analysis process. Lift force on a wing depends on chord length, angle of attack, flow velocity, and fluid properties. The angle of attack is defined relative to the free stream flow direction. Density, viscosity, and speed of sound also influence lift generation, especially under certain conditions. All these parameters can be combined into dimensionless groups. In this way, aerodynamic behavior can be analyzed in a more general manner. Dimensionless parameters. Some parameters, such as angles, are inherently dimensionless and do not require further manipulation. These parameters can be directly included in functional relationships as pi groups. This simplifies the analysis process because not all variables need to be processed algebraically. This concept also shows that not all physical parameters carry units. By recognizing this, the process of forming dimensionless groups becomes more efficient. Repeating parameters selection. The selection of repeating parameters is often the most difficult part of dimensional analysis. The right choice will make the process simple and the results clean. In contrast, a poor choice can lead to complicated algebra and results that are hard to interpret. Therefore, experience and practice play a major role in improving this skill. With more practice, intuition in choosing parameters will develop. Pipe wall friction. The wall shear stress in a pipe depends on flow velocity, wall roughness, and fluid viscosity. The inside diameter of the pipe and the roughness height affect the magnitude of flow resistance. Density and viscosity determine how the fluid interacts with the wall surface. All these parameters together determine the pressure loss due to friction. This problem is often analyzed using dimensionless numbers, such as the Reynolds number and friction factors.
Check your understanding. Number 10. What factors primarily influence wall shear stress in a fluid flowing through a pipe? B. The pipe's inside diameter, wall roughness height, fluid speed, and viscosity. Explanation. A is incorrect because temperature is not a direct factor in wall shear stress unless it affects viscosity, which is already a key factor. C is incorrect because wall shear stress is related to internal flow properties, not external geometry or external pressure forces. D is incorrect because while material composition affects pipe durability, it does not directly influence wall shear stress in the fluid.
Pipe flow friction factors. In pipe flow, the Darcy friction factor is commonly used to analyze pressure losses. The fanning friction factor is also used, but its value is smaller because of a different definition. The two are related through a simple proportional factor. It is important to know which definition is being used to avoid misinterpretation of data. This understanding is important in practical engineering calculations.
Velocity profiles in pipes. Axial velocity profiles are often normalized so they can be compared across different flow cases. CFD results show that the profiles for air and water can be plotted on the same graph. Differences in fluid properties affect the shape of the profiles, but in dimensionless form, the comparison becomes clearer. This approach demonstrates the power of normalization and non-dimensionalization. In this way, results from various conditions can be analyzed together. 2-pi plot analysis. In 2-pi analysis, one pi group is treated as the dependent variable, and the other as the independent variable. The resulting relationship can be a straight line or a curve, depending on the physical nature of the problem. Experimental data are often fitted using regression techniques to obtain a mathematical relationship. This approach is very common in experimental data processing. In this way, physical relationships can be expressed in a compact form. Wall shear stress comparison. The comparison shows that wall shear stress in water flow is much higher than in airflow. Nevertheless, the Darcy friction factor in dimensionless form can have the same value for both cases. These results are obtained from CFD simulations using a specific turbulence model. Flow velocity and fluid properties strongly influence the magnitude of shear stress. This example shows how dimensional and dimensionless quantities provide different perspectives.
Check your understanding number 11. This question emphasizes that the main differences between water and air flows lie in their viscosity and density. These two properties influence the magnitude of the shear forces at the wall. By answering it, students reconnect the concept of fluid properties with quantitative results. This problem also reinforces understanding of the role of physical parameters in flow. This short evaluation maintains continuity of understanding before moving to the next topic.
Wind tunnel drag measurement. Aerodynamic drag force is measured using a truck model inside a wind tunnel. A moving belt is used to simulate ground conditions to better approximate real situations. With this setup, the flow around the model becomes more representative of actual road conditions. Wind speed and surface conditions can be precisely controlled during testing. This approach allows systematic and repeatable evaluation of aerodynamic performance.
Wind and water tunnels serve similar purposes, but operate with different fluids. Water tunnels can reach higher Reynolds numbers at the same speed compared to wind tunnels. This is useful when simulating flow conditions that are difficult to achieve in air. In addition, flow visualization is often easier in water. The choice of testing facility depends on the objectives and limitations of the experiment.
Reynolds number independence. At sufficiently high Reynolds numbers, the drag coefficient becomes nearly constant and no longer depends on the Reynolds number. This condition is known as the Reynolds number independence region. In this region, test results from a model can be extrapolated to the prototype more reliably. In contrast, data at low Reynolds numbers are often unstable and unreliable. Therefore, choosing the appropriate Reynolds number range is very important.
Wind tunnel data insights. The data show that drag force increases as the flow speed in the wind tunnel increases. The tested speed range covers values from about 20 meters per second to 70 meters per second. Within this range, the drag force changes significantly from small to large values. These results are consistent with the theory that drag force strongly depends on flow speed. Such graphs help visualize the sensitivity of force to changes in speed.
Check your understanding number 12. What is the primary reason aerodynamic drag force increases with wind tunnel speed? C. The aerodynamic drag force is proportional to the square of the wind speed. Explanation. A. Incorrect because material properties are not affected by wind speed in this context. B. Incorrect because the drag coefficient typically remains constant for a given object at steady flow conditions, while drag force increases quadratically with speed. D. Incorrect because wind tunnel dimensions do not directly amplify drag force. The increase is due to the square relationship with wind speed.
Drag coefficient versus Reynolds number. This graph shows that the drag coefficient decreases sharply at low Reynolds numbers and then becomes nearly constant at high Reynolds numbers. The flat part of the curve indicates the Reynolds number independence region. These data come from wind tunnel tests of a truck model. This pattern explains why tests are often conducted at sufficiently high Reynolds numbers. In this way, the results are more reliable for prototype prediction.
Free surface flows and parameters. For free surface flows, both the Reynolds number and the Froude number are important. The Reynolds number represents viscous effects, while the Froude number represents the ratio between inertial and gravitational forces. In many cases, matching both numbers at the same time is very difficult, or even impossible. Therefore, compromises are often required depending on which phenomenon is most dominant. This shows the practical limitations in physical modeling.
Towing tank testing observations. Towing tank tests show how changes in the Froude number affect wave formation and flow patterns. At low Froude numbers, the generated waves are very small and the flow is relatively smooth. At intermediate values, more complex wave interactions begin to appear. At high values, wave effects become very strong and flow separation may occur. This example confirms the central role of the Froude number in free surface flows.
Scale model study insights. Scale model studies are used to simulate navigation conditions in a lock system with a 1:100 scale ratio. The model includes details such as the spillway, powerhouse, and existing lock structures. Distances in the model are scaled proportionally so that 52.8 feet in the model represents 1 mile in the prototype. By adding full-scale objects such as trucks, the perception of size becomes easier to understand. This approach allows the impact of new infrastructure and environmental changes to be evaluated safely and in a controlled manner.
Extrapolation in free surface flow experiments. In many free surface flow experiments, the Reynolds number and the Froude number cannot be matched simultaneously. Therefore, data from low Reynolds number models are often used to predict high Reynolds number prototype behavior through extrapolation. This approach relies on the assumption that the behavior trend is already stable in a certain range. Although not perfect, this method is often the only practical way. This shows both the limitations and the creativity in engineering experiments.
Check your understanding number 13.
This question emphasizes the concept of extrapolation as a tool to predict prototype behavior from model data. The key answer is that low Reynolds number data are used to estimate high Reynolds number conditions. By answering it, students strengthen their understanding of practical strategies and experiments. This problem also reaffirms the limitations of perfect similarity in the real world. This short evaluation ties together the whole modeling concept into a single idea.
References. This section lists the main source of figures and materials used in this chapter, namely the textbook by Chengal and Chimbala. This reference shows that the discussion is based on a standard textbook widely used worldwide. By knowing the source, students can deepen the material independently through further reading. It also emphasizes the importance of academic ethics in citing references. This closing slide ends the whole discussion on dimensional analysis and modeling.